In this video, I'd like you to open your notes to page 23 as we discuss a little bit more one of the problem areas of 7.2, which is when we rotate around a line that is not the end of the y-axis. And then the third example, if I have time to get to it, because I'm only going to make one video, we'll be doing a full region that's the intersection of two regions. So we're going to try to hit two problems areas here. So on this one, we are rotating about the line x equals 5, which is a vertical line. So our first task is to graph. And so right here I have my line of rotation, and I'm going to be rotating this way. And the function that I'm working with is the square root function, which is an easy one. And we have it solved for y, so we know the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and we get this parent function for the square root. And so the region that we are working with is bound by y equals 0, which is the x-axis, and by x equals 4, which is this vertical line. So we are going to be revolving this region in here. Go see if I can shade it in a little bit here. About the vertical line, x equals 5. So let's begin here with this one. The first thing we need to do is draw what we call our representative rectangle. And we always draw it perpendicular to the axis of rotation. So for this one, I'm just going to hop right in here and draw what we call our representative rectangle. And it can be of any width. Keep in mind what we eventually are considering is an infinite amount of them, which are infinite skinny, so we're actually going to be making them kind of going like this, but just for these purposes, we're going to blow it up a little bit, and you'll notice that this right here is what we would call delta y, a change in y, and when we do it infinitesimally small, we call it a differential in y, or dy. But this is what we would call a dy problem, and also, because I have a gap here with my axis of rotation, when I rotate, I'm going to have what we would call a washer. So our first task is, first of all, we graph. Then we draw a representative rectangle that runs perpendicular to the axis of rotation. We decide if we have a dy problem or a dx problem, a washer or a disk. So when we have a washer problem, we need two pieces of information. We need what we call capital R, the outer radius. And to get that, remember, we draw a line from the axis of rotation to the outer edge of the region that we're rotating. Edge. Let me get that in there. Alright, so when we're talking about capital R, it's really important for you to note that capital R is from the axis all the way across. And you know, it changes as I move up and down this region. So I have to write it generically in terms of a point. Well, you'll notice that this is a dy problem, so everything needs to be in terms of y. So what I need here is I need to say x in terms of y would be y squared. And so that when I write a point, I have the point written in terms of y, and that's kind of difficult for some kids to understand. So I'm going to repeat what that kind of means here, and I'm going to take a point that's easy to see on this curve. On this point, if x is 4, y is the square root of x, which is 2. So this is the point 4 comma 2 if we write it in terms of x, which would be x square root x. Now if we write it in terms of y, what that means is if you are given the 2 for y, how do you get the x? And you'd say, well, you square it. And so we would say that this is the point y squared comma y. You're so used to dealing with f of x that the concept of f of y is kind of new. So when I put this point on here, I'm going to call it y squared comma y, not x comma f of x. They both result in the same numerical point. But when I have a dy problem, I want everything, limits, points, radii, everything in terms of y. So when I'm looking for my capital R drawn from the axis to the outer edge, I have to figure out, well, what is my capital R? It's from here to the outer edge. Well, this piece right here is y squared, from the origin to the point on the curve. So in order for me to get that the length of capital R, I would have to take 5 minus y squared. And so my R is 5 minus y squared. The inner radius is a little easier, and that's drawn from the axis to the inner edge of the region that you're rotating. And that doesn't change as I rotate it. That's locked in all the way on here. No matter where I draw my representative rectangle, we would say that little r is 1. It's just from 4 to 5. So that's a little easier. Now, when we rotate it, we get this solid right here created. And it's got, you can see right in here, it does have a hole in it. And so each one of these is going to create a washer. And we are going to sum them all up. And here's our formula for it. And let's set it up, and then you can math 9 it if you want, but for time purposes, I would like to move on and not do the arithmetic. So my volume is equal to pi times the integral. Now again, this is a dy problem. I'm going to be summing up these rectangles from bottom all the way up to the top. So it's going to go from 0 up to the y value, from 0 to 2. And then I do my big R squared, which would be 5 minus y squared, quantity squared, minus little r squared, which would be 1 squared, and then dy. Now, if I had to do this by hand, I'd FOIL this out, I'd subtract 1, I'd use the fundamental theorem of calculus to evaluate it, but for time purposes, I'm just going to tell you what the answer is. It'd be 416 pi over 15, and I would like you to make sure you could do the work to arrive at that answer. So what I'm going to do on the next page here is we're going to do the same problem, but we're going to change that axis of rotation. We're going to rotate it about the horizontal line, y equals -1. So right here is going to be, oops, sorry, I didn't mean to move that over, right, just a minute, scoot that back. My axis of rotation is now this line right here, and I'm going to be pulling it this way about the line y equals -1. My process is the same. I start with a representative rectangle drawn perpendicular to the axis of rotation. I like to kind of pretend it's on a little stick here. And then I notice that this right here is what we'd call a dx, a change in the x-axis, a differential of x. I'm also got a gap with my axis of rotation, so this would be a dx problem. It would also be a washer and not a disk. So likewise, with the last problem, I need my capital R. My capital R is the distance from my axis to the outer edge. Now this one I want everything in terms of x. So that point is considered x comma square root x. That's how high it is, and I want that in terms of x because I've got a dx problem. So, and again with a point, if you kind of look at it, remember this was the point 4 comma 2. If I was looking for how far this was, I'd say, well, it's the 2 from the x-axis, plus this one. Well, that's exactly how I get my capital R in general for wherever I drew my representative rectangle. I would have 1 to get from here to here, and then from the x-axis to the curve is the square root of x. So big R is 1 plus the square root of x. Little r is easy on this one because it's just this gap with my axis of rotation, which is 1. So when I set this up using my format for my washer dx problem, and again here's the solid created when you generate that, you can see it's going to have this hole created in here, and we'd have all these washers that we're summing up along the curve, creating the total volume. So my volume is going to equal pi times, now we're going in terms of x, so I want my limits in terms of x. I will be integrating from here all the way over to here, drawing vertical rectangles, which means I'd go from 0 to 4. And then I do capital R squared, which was 1 plus the square root of x, quantity squared, minus little r squared, and then this is a dx problem. And again, normally you're allowed to math 9 it, but make sure you would know how to do it by hand. So moving on to the next one I'd like to discuss, and I don't know if I'll have time to get the whole thing done, but we're going to go look at number 7. If you understand this one, this is about as hard as they get. So let's again start with our sketch. In order to do our sketch, we need to kind of solve these for y so we know what their graphs look like. So my first thing is going to be to take x equals y squared minus 4 and solve it for y. I'm going to add 4. I'm going to take the square root, and whenever I do that, I do plus or minus. So my first function, I'm going to call it y1, is the square root function starting at -4, 0, and it would go to 0, positive 2, 0, negative 2, and you should know that your square root general graph looks like this. Don't forget the negative part of it, that's very common. If you're allowed to use your calculator, make sure again you still need to algebraically include that plus or minus and then enter it as 2 separate pieces. For my other function is x equals 6 minus 3y. This is going to be linear. I'm going to solve it for y. I get x minus 6 equals negative 3y. I divide everything by negative 3. And so really this is a line with a y-intercept at 2 and a slope of negative 1/3. So it's going to hit right here. I've got an intersection. It's going to go down 1 over 3. My line's going to head like this. All right, now so that's my first step. I need a graph. In order to graph, we must solve for y. Now, I've got to take a look and see what my axis of rotation is. It's the line x equals 24, which is a vertical line. So I'm going to draw that. I'm going to be rotating this way. And my region for rotation, if I were to color it in nicely here, would be this green piece. And I'm going to whip it around this way, creating a solid. So my next step, once I determine the region, is to go ahead and draw my representative rectangle. And they need to be drawn perpendicular to the axis of rotation. So it's going to be a horizontal rectangle. And again, I kind of like to put it on a stick all the way over here. And I will again notice that this is a dy problem. My differential is along the y-axis. So I've got a dy problem. It's a washer problem. And now I am ready to start. In order for me to figure out this, I am going to be integrating. I'm going to be integrating this way when I make my horizontal rectangles of an infinitesimal width. And what I'm going to be doing then is going from low to high, r squared minus r squared, both in terms of y, dy. And most common thing kids forget with these is the pi out front in all of the work. So kind of make sure that's my general format. I only have 2 minutes left, so I'll get as far as I can and then we'll maybe discuss it later. So my outside radius is or my big R, from the axis to the outer edge of the curve. Well, what is that? In terms of y, these are actually already in terms of y. That's y squared minus 4, comma y. That's what this point would be. It's negative over there. And so to get the distance for capital R, I would say it's 24 minus the x value, which is y squared minus 4. When I do the arithmetic on that, I get 28 minus y squared. That's my capital R. My little r runs from the axis to the inner edge. And this point, in terms of y, the x is 6 minus 3y, comma y. That would be the full 24. Watch when I draw this. It'd be the full 24 minus that x value. So my little r would be 24 minus 6 minus 3y. Doing the arithmetic on that, I'd get 18 plus 3y. So when I set this up, and I think I'll have time to set it up, I've got pi goes from low to high. I know this high was at 2. How do I find the low one? I'll do that in a minute. I want to set this up though. I'd have big R, which is 28 minus y squared, minus baby r, which is 18 plus 3y, quantity squared dy. My only thing I need is this bottom limit. And to find that, like we did in class, we set the two functions equal. And when I write this as a quadratic here, you might have to slow this down because I've only got 15 seconds left. When I factor it, I'm sorry, that'd be a plus, I'm going to get a y plus 5 and a y minus 2. So my intersection points are at 2, bam, and negative 5.